You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Infrastructure as Code, often shortened to IAC, has reshaped the way organizations provision and manage cloud resources. Instead of manually configuring systems through consoles or command line tools, engineers describe infrastructure in code, using templates and scripts that can be stored, reviewed, and tested like any other software artifact. The purpose of this approach is to make environments reproducible, consistent, and governed by version control. When done securely, IAC also enforces compliance, limits human error, and provides auditable change history. This approach turns what was once an ad hoc, error-prone process into a disciplined workflow. For learners, the promise of IAC is not simply automation for speed, but automation for assurance, where every resource can be recreated from code, every change explained in records, and every deployment aligned with organizational policies and security frameworks. At its core, IAC expresses infrastructure in code so that environments are reproducible, reviewable, and testable. Instead of treating infrastructure as a black box, it is treated as a blueprint that can be inspected and improved collaboratively. For example, spinning up a new application environment becomes as simple as executing a template, which guarantees consistency with prior environments. This reduces the risk of snowflake servers that drift from standards because of manual configuration. Code-driven infrastructure also integrates with testing and version control, making infrastructure changes as accountable as application code. This shift allows developers, operators, and security teams to collaborate more effectively, aligning infrastructure changes with organizational goals. It represents not just a technical evolution but also a cultural one, bringing infrastructure into the shared practices of modern software engineering. Declarative models are the dominant paradigm in IAC, where engineers specify the desired state of resources rather than writing step-by-step instructions. The IAC engine, such as Terraform, CloudFormation, or ARM templates, figures out how to reconcile actual state with the desired one. This abstraction reduces complexity, letting teams focus on outcomes rather than procedures. For example, declaring that 3 virtual machines should exist in a subnet leaves the engine to determine whether to create, delete, or update instances as needed. Declarative approaches reduce the likelihood of errors caused by overlooked steps in imperative scripts. They also enable drift detection, as the engine compares reality with the declared blueprint. By relying on declarative models, organizations move closer to intent-based infrastructure, where consistency and security come from automated reconciliation rather than manual vigilance. Idempotency is a foundational principle of IAC, ensuring that applying the same code multiple times yields the same result without unintended changes. Without idempotency, repeating deployments could lead to duplicate resources or unexpected reconfigurations. For instance, if a template specifies a single load balancer, applying it repeatedly should not create new ones each time, but should confirm the existing one remains in place. Idempotency supports stability by making operations predictable, which is especially critical in automated pipelines. It also provides confidence in recovery scenarios, as environments can be rebuilt or reapplied without fear of compounding errors. In practice, idempotency means that IAC is not just about provisioning, but about enforcing desired state continuously, reducing drift, and ensuring that infrastructure reflects approved templates over time. Version control systems provide the governance layer for IAC, tracking every change to templates and enabling collaborative workflows. With Git repositories, infrastructure definitions gain history, branching, and the ability to review changes before they are applied. Pull requests bring peer review into the process, allowing security and operations teams to weigh in on changes before they reach production. Version history also supports auditing, showing exactly when and why a resource was modified. For example, if a firewall rule changes, The commit log provides evidence of who made the change and the justification. This accountability transforms infrastructure management into a transparent process where no change is hidden and every update can be explained. By leveraging version control, organizations align infrastructure with the same rigor that governs application development. Modules and reusable components streamline IAC by encapsulating common stacks into standardized building blocks. Instead of rewriting templates for every project, teams can call modules with predefined inputs and outputs. For instance, a networking module might provision a virtual network with subnets, routing tables, and access controls. By reusing modules, organizations ensure that patterns are consistent and security best practices are embedded from the start. Modules also simplify review, as standardized components can be vetted once and trusted across many deployments. This approach improves efficiency while reducing the chance of introducing insecure configurations in ad hoc templates. Like libraries and software engineering, modules represent the codification of institutional knowledge, making IAC more maintainable, scalable, and secure. Environment separation enforces discipline by isolating development, test, and production environments. Each environment has distinct state files, access controls, and approval processes. This prevents changes intended for experimentation from accidentally reaching production systems. For example, developers may have broad access in development but only read access in production, with changes requiring peer review and approvals. Separation also supports compliance, as regulated environments can enforce stricter policies. In IAC, this principle is realized by parameterizing templates and associating them with distinct environments, ensuring consistency without blending privileges. Environment separation reinforces the idea that not all resources carry equal risk, and that governance must reflect operational reality. State management is one of the most sensitive aspects of IAC because it tracks the mapping between declared code and actual resources. State files often contain identifiers, metadata, and sometimes secrets, making them high-value targets. Securing state requires encryption, access controls, and locking mechanisms to prevent concurrent modifications. For example, Terraform supports state locking to ensure that two engineers cannot apply conflicting changes simultaneously. Storing state in secure backends, such as encrypted object stores with restricted access, reduces exposure. Without disciplined state management, IAC becomes unreliable, as changes may conflict or leak sensitive information. With it, state becomes a controlled artifact that enforces consistency and accountability across teams and pipelines. Secrets handling in IAC demands care, as hard-coding passwords or tokens into templates creates dangerous exposures. Instead, templates should reference secrets dynamically from vaults or secure variable stores. For example, an IAC script might pull a database password from a secret manager at runtime rather than embedding it in plaintext. This reduces the risk of secrets being committed to version control or appearing in logs. By integrating secrets management with IAC, organizations unify two critical disciplines, automation and security. Proper handling ensures that IAC delivers on its promise of repeatable deployments without creating hidden liabilities that attackers can exploit. It reinforces the broader lesson that automation must never come at the expense of protecting sensitive values. Code review ensures that infrastructure changes are vetted before application, bringing human judgment into the loop. Reviews may include peer approvals, automated linting, and rationale captured in change records. For example, before a new virtual network is deployed, reviewers might confirm that subnets align with organizational standards and that no broad allow-all firewall rules are introduced. Automated checks complement human review, flagging policy violations or insecure configurations. Code review enforces collective responsibility, ensuring that no single engineer can introduce risky changes unilaterally. In cloud environments, where mistakes can propagate instantly, peer review provides a buffer of oversight, blending automation with accountability. Linting and static analysis tools add a preventative layer by scanning IAC templates for syntax errors, style inconsistencies, and provider-specific best practices. These tools act like compilers for infrastructure, catching issues early in the development lifecycle. For example, a linter may flag an insecure configuration, such as an unencrypted storage bucket, before it is ever deployed. Static analysis extends further by checking for policy compliance, such as requiring tagging or disallowing public endpoints. By integrating linting and static analysis into CI pipelines, organizations ensure that insecure or non-compliant code is blocked automatically. These tools transform quality control from a manual review burden into a continuous automated safeguard. Testing applies software engineering discipline to IAC, verifying that templates behave as intended. Unit tests validate individual modules, while integration tests evaluate how components interact in staging environments. Post-deployment assertions confirm that resources match expectations, such as verifying that a firewall only allows traffic from specific ranges. Testing reduces the risk of errors and provides confidence that changes are safe to apply. It also creates reusable validation logic, ensuring that new deployments conform to the same standards as existing ones. Without testing, IAC becomes a trust exercise. With testing, it becomes a reliable, repeatable process grounded in evidence. Drift detection monitors for differences between deployed infrastructure and declared templates, alerting teams when unauthorized or manual changes occur. Drift erodes confidence in IAC because it means that the source of truth no longer reflects reality. For example, if someone modifies a firewall rule directly in the console, drift detection highlights the discrepancy. By reconciling drift through code, organizations restore integrity and prevent configuration sprawl. Drift detection reinforces the discipline of IAC. Infrastructure should always be managed through code, not manual edits. It provides early warning when processes are bypassed, ensuring that governance remains intact. Immutable infrastructure embraces replacement over modification, reducing configuration variance over time. Instead of updating servers in place, new ones are provisioned from templates and the old ones are retired. This eliminates the accumulation of configuration drift and ensures that all instances reflect current baselines. For example, rather than patching a virtual machine repeatedly, a new machine is created from the latest hardened image and swapped in. Immutable practices simplify rollback, as older versions remain available for redeployment. They also strengthen security by removing hidden dependencies and untested variations. Immutable infrastructure aligns perfectly with IAC's goal of consistency, ensuring that deployments remain faithful to their declared templates. Architecture decision records and supporting documentation provide the context behind IAC templates. ADRs capture why certain choices were made, the constraints considered, and the trade-offs accepted. READMEs explain how to use modules, their inputs, and expected outputs. Together, this documentation ensures that templates remain understandable and maintainable over time. For example, if a team decides to enforce private endpoints for storage, the ADR records the rationale, helping future engineers understand the choice. Documentation transforms IAC from opaque scripts into transparent systems where decisions are explicit and traceable. It strengthens both collaboration and compliance, ensuring that infrastructure is not only coded but also justified. Artifact registries provide centralized repositories for storing version modules and templates, along with metadata for provenance and trust. These registries allow teams to pull vetted modules consistently, rather than relying on ad hoc or unverified sources. Provenance metadata tracks who created a module, what it includes, and whether it has passed security reviews. For example, an organization might maintain a private registry of approved networking modules, ensuring that developers only consume trusted artifacts. Registries also simplify updates, as new versions can be distributed with clear change histories. By treating modules as artifacts, organizations professionalize IAC, making it not just a collection of scripts, but a managed, Auditable ecosystem. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Policy as Code elevates infrastructure governance by embedding rules into automated enforcement engines. Instead of relying on human reviewers to catch misconfigurations, frameworks like Open Policy Agent evaluate IAC templates against codified rules before deployment. These rules can require encryption on storage resources, prohibit public-facing subnets, or enforce tagging standards. For example, a policy engine may reject a plan that attempts to deploy a database without encryption enabled. By expressing governance as code, organizations ensure that guardrails are applied consistently and automatically. This reduces friction for developers as they receive immediate feedback rather than post-deployment audits. Policy as Code also creates an auditable, testable layer of assurance, demonstrating that security and compliance are built directly into infrastructure workflows. It transforms governance from a reactive process into a proactive safeguard embedded in the development pipeline. Pre-commit hooks provide an even earlier enforcement point by running checks before IAC code is committed to version control. These hooks block secrets from being embedded in templates, catch insecure configurations, and prevent policy violations from ever entering repositories. For example, a pre-commit hook might scan for hard-coded API keys or block a commit that includes an overly permissive firewall rule. By catching issues at the developer's workstation, pre-commit hooks reduce downstream remediation costs and prevent sensitive values from leaking into history. This lightweight but powerful measure shifts quality control to the very start of the workflow. It demonstrates how security can be embedded seamlessly into development practices, complementing later pipeline checks with fast, localized safeguards that keep insecure code from progressing any further. Continuous integration pipelines play a central role in validating IAC changes before they reach production. Each commit or pull request can trigger automated pipelines that lint templates, run static analysis, validate policies, and generate deployment plans. These pipelines act as a safety net, ensuring that insecure or misconfigured templates are flagged automatically. For example, CI may detect that a proposed change creates a storage bucket without access restrictions and block the merge. CI pipelines also generate plan outputs, showing reviewers exactly what changes will occur if applied. This transparency improves collaboration and provides stakeholders with visibility into risks before approval. By making validation automatic and repeatable, CI ensures that IAC changes move through a rigorous filter, reducing human error while strengthening confidence in security and compliance. Continuous delivery pipelines extend automation into deployment, applying approved plans under controlled conditions. These pipelines respect governance processes by including windows for execution, formal approvals, and rollback capabilities. For instance, a CD pipeline might apply infrastructure changes only during maintenance windows, requiring sign-off from security or operations leads. Rollback mechanisms ensure that if problems occur, environments can be reverted safely to their prior state. CD pipelines enforce discipline in how infrastructure is applied, replacing ad hoc console edits with controlled, auditable processes. By aligning automation with governance, CD demonstrates that agility does not require abandoning oversight. Instead, it shows that speed and security can coexist, provided workflows are designed to balance automation with structured control. Least privilege runner credentials are essential for securing CI/CD pipelines. Pipelines themselves often have powerful access, making them prime targets for attackers. To reduce risk, runners should be provisioned with narrowly scoped credentials that permit only the actions necessary for their tasks. For example, a pipeline that deploys resources in a staging environment should not hold permissions for production accounts. By limiting access, organizations reduce the potential impact if pipeline infrastructure is compromised. Least privilege credentials also align with compliance frameworks that mandate segregation of duties. In practice, this requires careful design of service accounts, roles, and policies, ensuring that automation is both empowered and constrained. Runner credentials highlight the reality that pipelines are not just tools but privileged actors requiring governance as rigorous as that applied to human administrators. Artifact signing strengthens trust in IAC by attesting to the integrity and authenticity of modules and templates. By cryptographically signing artifacts, publishers can prove their identity, and consumers can verify that code has not been tampered with. For example, a signed networking module retrieved from a registry provides assurance that it was created by an approved team and has not been altered in transit. Verification is automated during pipeline execution, blocking unsigned or invalid artifacts. This practice aligns with broader supply chain security, where provenance and integrity are critical to defending against tampered dependencies. Artifact signing turns IAC modules into verifiable components, making trust explicit rather than assumed. It ensures that infrastructure is built only from vetted, authentic building blocks, reducing exposure to supply chain attacks. Golden module catalogs provide organizations with curated, vetted building blocks for common infrastructure patterns. These catalogs offer reusable modules that encapsulate security best practices, operational standards, and compliance requirements. For example, a golden module for deploying a web application might include private networking, encryption, and logging by default. Teams that use the module automatically inherit these protections without needing to reinvent them. Catalogs also establish ownership, with designated teams responsible for maintaining modules, applying patches, and updating documentation. By consuming modules from a trusted catalog, development teams gain both efficiency and assurance. Golden catalogs reduce duplication and inconsistency, ensuring that infrastructure deployments are not just rapid but also secure, standardized, and supportable across the organization. Multi-account or multi-subscription strategies provide another guardrail, partitioning cloud environments to reduce blast radius and delegate administration. Instead of centralizing all resources in a single account, organizations separate workloads by function, environment, or business unit. For example, production, staging, and development may each reside in distinct accounts with their own billing and access policies. This prevents misconfigurations in one area from cascading across the entire organization. Delegated administration also allows local teams to manage their resources without jeopardizing enterprise-wide governance. IAC templates encode these strategies by provisioning accounts and linking them with organizational policies. By designing partition structures, organizations reinforce both security and resilience, ensuring that incidents remain contained and governance remains distributed yet consistent. Tagging and metadata standards bring order to sprawling infrastructures by attaching ownership, cost, and compliance attributes to every resource. Tags may include cost center identifiers, application owners, environment labels, or regulatory designations. For example, every resource in a healthcare environment may carry a compliance tag indicating whether it handles protected health information. IAC templates can enforce tagging standards automatically, preventing untagged resources from being deployed. Metadata also supports automation, enabling cost reporting, security scans, and governance policies that rely on consistent labels. By embedding tags into IAC, organizations ensure that infrastructure is not only provisioned, but also contextualized. This practice transforms resources from anonymous objects into accountable assets, traceable across financial, operational, and compliance dimensions. Change management integrates traditional governance with automated IAC workflows. Pull requests link directly to tickets, risk assessments, and stakeholder approvals, ensuring that infrastructure changes are justified and reviewed. For example, a proposed security group modification might require documented approval from both application and security teams. Automated pipelines enforce that only approved code is merged and applied, reducing opportunities for bypass. Change management does not disappear in IAC. It evolves to match the speed of automation while preserving oversight. By embedding governance into pull requests and pipelines, organizations maintain accountability without slowing innovation. This integration ensures that IAC remains both agile and compliant, balancing rapid delivery with disciplined control. Observability in IAC provides visibility into the provisioning lifecycle by emitting plan differences, apply logs, and policy enforcement results to centralized logging systems. These records create a transparent view of what was proposed, what was applied, and whether policies were followed. For instance, logs may show that an attempt to deploy an internet-facing load balancer was blocked by policy. Centralizing observability supports both troubleshooting and compliance, as auditors can trace changes end to end. Observability transforms IAC from a black box automation tool into an open, accountable system. It ensures that provisioning is not only automated, but also explainable, enabling both operational learning and regulatory assurance. Rollback and break glass procedures define how organizations recover when automated deployments go wrong. Rollback plans specify how to revert infrastructure to a safe prior state, often using immutable templates or versioned artifacts. Break glass procedures provide emergency overrides, granting temporary elevated access to remediate urgent issues. For example, if a deployment locks out administrators, a break glass account may be used under strict monitoring to restore access. These procedures balance resilience with accountability, ensuring that rapid fixes remain governed and time-limited. By planning for failure, organizations prevent incidents from escalating into prolonged outages. Rollback and break glass practices reinforce the reality that security and availability must coexist, with safeguards in place for both normal and emergency conditions. Evidence generation ensures that IAC practices are defensible in audits and compliance reviews. Exported plans, approval records, and policy evaluation results can be mapped to frameworks such as SOC2, HIPAA, or PCI DSS. For example, evidence might demonstrate that all storage resources were deployed with encryption enabled, enforced by policy as code. Automating evidence collection reduces manual burden and ensures consistency, transforming compliance into a byproduct of daily operations rather than an ad hoc scramble. Evidence generation strengthens trust with regulators, customers, and leadership, proving that IAC not only accelerates operations but also embeds security and governance at its core. Anti-patterns in IAC highlight what to avoid in order to maintain security and integrity. Manual console edits undermine reproducibility and create drift, breaking the principle of code as the source of truth. Long-lived administrator credentials in pipelines create persistent risk, offering attackers a valuable target. Unreviewed drift, where runtime changes differ from declared templates, erodes confidence and governance. These anti-patterns often arise from shortcuts or legacy habits, but undermine the very benefits IAC is designed to provide. By recognizing and correcting them, organizations maintain discipline, ensuring that IAC remains a controlled, auditable system rather than a chaotic patchwork. Avoiding anti-patterns is as important as adopting best practices, as it prevents regression into insecure or unmanaged infrastructure. For exam preparation, the relevance of IAC lies in selecting appropriate guardrails, enforcing least privilege, and applying testing strategies to secure provisioning workflows. Candidates should understand how policy as code, pre-commit hooks, and CI/CD validation strengthen governance. They should also recognize the risks of anti-patterns and how to remediate them through immutable infrastructure, drift detection, and proper state management. Exam questions may test knowledge of how to integrate secrets management, tagging standards, or golden module catalogs into workflows. The emphasis is on ensuring that IAC does not simply automate provisioning, but does so in a way that is secure, consistent, and auditable. In summary, infrastructure as code transforms cloud provisioning from manual operations into governed, repeatable workflows. Secure IAC practices embed policy guardrails, enforce testing, and apply least privilege principles across automation pipelines. By leveraging artifact signing, golden module catalogs, and tagging standards, organizations build environments that are consistent and accountable. Observability, rollback plans, and evidence generation provide the transparency and resilience needed for compliance and operational trust. Avoiding anti-patterns ensures that automation delivers security rather than bypassing it. Ultimately, IAC is not only about speed but about creating cloud environments that are consistent, auditable, and secure, where every deployment aligns with both business needs and regulatory obligations. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.